The dark side of the moon is a phrase that's widespread in common parlance, thanks not least to a certain mega-selling Pink Floyd LP from 1975. But does the moon really have a dark side? That depends on what you mean by dark. Pause for a few seconds and support me with a subscribe. If you mean, does the moon have one side that is in permanent darkness? Then the answer is no. While one side of the moon permanently faces towards Earth, and one permanently faces away, both sides receive pretty much equal quantities of sunlight over the course of any given year. There is no dark side of the moon, because there is no side of the moon permanently shielded from sunlight. But dark has other meanings. One of these, per the Merriam-Webster dictionary, is not known or explored because of remoteness, which is one reason why the moon's far side is often, perhaps misleadingly, called the dark side. In more recent times, another sense of the word dark has emerged. People who suddenly aren't available through the normal communications channels can be said to have gone dark. This meaning, too, can be fairly applied to the lunar far side, because the moon blocks radio signals sent to or from any craft that's orbiting there. Perhaps in some sense, you can talk about the dark side of the moon. All the same, astronomers, to avoid confusion, talk about the far side of the moon rather than the dark side. The reason the moon has a far side at all is due to a gravitational phenomenon called tidal locking. Gravity keeps the moon at such a distance from Earth that it takes 28 days to orbit our planet. But 28 days is also how long it takes the moon to rotate once on its axis, which is why one side of the moon is always facing Earth, and one side is always facing away. This, by the way, is actually quite a common phenomenon. Within our own solar system, Mercury is tidally locked to the Sun, while other tidally locked satellites include, among others, Mars's moons Phobos and Deimos, Neptune's moons Proteus and Triton, Pluto's moon Charon, and too many of Jupiter, Saturn, and Uranus's moons to list here. Back to our own moon, though, and it should be pointed out that the tidal locking described above is not a perfect system. Slight variations in the Earth-Moon distance cause a phenomenon called lunar libration, an apparent oscillation of the moon as seen from Earth. And thanks to libration, some far-side regions that lie very close to the terminator, the putative dividing line between the near and far sides, are occasionally visible from Earth. These include Mare Oriental and Crater Einstein. Such regions make up around 18% of the lunar far side surface area. The other 82% is forever out of sight, or at least, it was until the first lunar orbiting missions, both Russian and American, in the late 50s and early 60s. Since then, the whole of the far side has been photographed and mapped by orbiting spacecraft. More recently, 2 missions have actually touched down there, China's Chang'e 4 in 2019 and Chang'e 6 in 2024. With NASA's Artemis 3 due to follow in 2026, scientists are interested in the far side, partly because its topography is quite different from that of the near side, with lots more impact craters and basins, and far fewer smooth, flat mare regions. And partly because there is growing interest in the idea of eventually constructing a radio telescope there. That's because such a telescope would be facing out into space and be shielded by the moon's sheer bulk from any signal interference originating from Earth. We'll see if that ever happens. But in the meantime, here's a fun fact to end on. As we've already said, both sides of the moon receive a roughly equal amount of direct sunshine per year. But like all the best stories, that seemingly simple tale contains a couple of twists. Firstly, the near side of the moon, unlike the far side, is also exposed to sunlight that's been reflected off Earth. Just as here on Earth we get moonlight, that's really sunlight reflected off the moon. In fact, a full Earth, as seen from the moon, is 34x brighter than a full moon seen from Earth. But there's another factor to take into account, which is that the near side of the moon is regularly occulted, at least in part, by Earth's shadow. That's what we on Earth call a lunar eclipse. But that doesn't happen on the far side, of course, because it's facing away from us. The end result of all this, when you add up all the hours of direct and/or indirect sunlight exposure and subtract any time spent in Earth's shadow, is that, far from being dark, the lunar far side actually receives slightly more sunlight in any given year than the near side does. Let's pause for a few seconds and give me a like for this video. Thank you so much. The high-rate excavation needed to harvest helium-3 from the moon in large quantities has never been attempted before, let alone with high efficiency. We just got our first look at a prototype for a novel moon mining machine. When you're operating equipment on the moon, reliability and performance standards are at a new level, Rob Meyerson, co-founder and CEO of the Seattle-based startup Interloon, said in a May 7th statement. The machine is designed to churn up 110 tons of lunar dirt, or regolith, per hour to harvest helium-3, a potential fuel source for future fusion reactors. Helium-3 is rare on Earth, but is thought to be plentiful on the moon. The high-rate excavation needed to harvest helium-3 from the moon in large quantities has never been attempted before, let alone with high efficiency, Gary Lay, Interloon co-founder and chief technology officer, said in the same statement. Building the prototype fostered a unique partnership between Interloon and Vermeer, a 70-year-old agriculture and industrial equipment manufacturer. We've been very pleased with the results of the test program to date and look forward to the next phase of development, Lay added. Interloon said that excavation is the first step in a planned 4-step system to harvest natural resources from space: excavate, sort, extract, and separate. The startup went forward with building the full-scale prototype after successfully testing a smaller version of the machine last year. As a potential game-changing fuel source that could be used in a range of industries in the future, helium-3 and getting it from the moon to Earth has been a hot topic for years, and there have been American, Chinese, and Japanese efforts centered around mining the rare helium isotope. However, the cost of harvesting helium-3 and then delivering it for use on Earth could make it cost-prohibitive as a fuel source in the immediate future, according to Ian Crawford, professor of planetary science and astrobiology at Birkbeck, University of London. In 2021, Crawford told Space.com that the enormous amounts of investment and infrastructure necessary for the mining, extraction, and transportation of lunar helium-3 means that energy sources here on Earth may be cheaper for a while. Interloon and Vermeer are part of a larger wave of companies and organizations that are looking to help pave the way for future industries on and around the moon. For example, the U.S. Defense Advanced Research Projects Agency, DARPA, put forth its 10-year Lunar Architecture, Luna 10, capability study in 2023 and selected 14 companies to provide ideas about how to develop a lunar economy. Since 1969, the return of a human mission to the moon has never seemed so close. Although scientific interest continued to flourish, space programs had for many decades abandoned it in favor of the International Space Station and missions to explore the solar system. Dominated by the growing competition between the United States and China, the return to the moon is now motivated by a desire to study and possibly exploit resources that can be found there. Of these, helium-3 represents the most significant potential in the field of energy. This non-radioactive isotope is an ideal fuel for the operation of a fusion reactor. It consists of fusing helium-3 with deuterium, with the advantage of not producing neutrons. Whilst it is still in its experimental stages, the ability to contain such energy in the reactor's containment chamber could make it a viable energy source. In September 2021, U.S. company Commonwealth Fusion Systems, based in Massachusetts, announced the creation of a 20 Tesla magnetic field using a high-temperature superconducting electromagnet, which constitutes a remarkable advance. From this perspective, the extraction of helium-3 on the moon could facilitate the development of this breakthrough technology. As early as 1988, a NASA report on helium-3 mentioned the potential of this isotope for use in a nuclear fusion reactor. Theoretically, it offers several advantages compared to current nuclear power, as an abundant low-carbon energy and no nuclear waste technique. On paper, its advantages make it a competitive resource, while this isotope is useful for other applications including cryogenics, quantum computers, and MRI lung imaging. Also, the Moon is its main reservoir. For billions of years, the action of solar wind has released high-energy particles, including helium-3, which has accumulated on the Moon in the absence of an atmosphere. A renewable resource by definition, the isotope is regularly deposited on the Moon's surface under the constant activity of the Sun. However, as Ian Crawford shows, the notion of the abundance of this resource must be weighed up. The highest concentration observed in measurements carried out on samples is 10 parts per billion, depending on the mass, for an average concentration of 4 ppb in the regolith layer. As a prerequisite for the installation of a human base, many states, India, Russia, China, United Arab Emirates, etc., are preparing new lunar missions in the coming years. By far, the Artemis program, supported by NASA, is the most successful at this stage for this planned return. Alongside the United States, many countries such as Australia, Brazil, Italy, Japan, and Luxembourg have joined this ambitious project. China, together with Russia, is also considering the establishment of a lunar base. However, the specifications for such an undertaking remain incomplete for the time being, both in terms of the financial resources and the technical arrangements to reach the target set for 2030. Clearly, a permanent installation requires the construction and maintenance of infrastructure through the use of locally available resources and the intensive use of robots. In this regard, the Australian company Lighton is looking to deploy 3D printing technology to provide on-site construction solutions. In other words, the aim is to implement an artificial lunar ecosystem to facilitate travel to Earth. To achieve this ambition, the French incubator TechTheMoon, based in Toulouse, is the first in the world dedicated to developing a permanent settlement on the Moon. Despite this emulation, the establishment of a human colony remains a distant prospect. A recent NASA audit report points to cumulative delays in the Artemis program, particularly in the development and testing of the lunar module, which de facto postpones the mission beyond 2024. China has demonstrated a meteoric rise in its space activities heading towards the Moon, both economically and technologically. As a fundamental step in the development of its space program, China sent its first probe into orbit around the Moon in 2007. Since then, the Chang'e 4, 2018, and Chang'e 5, 2020 missions have made significant progress in the knowledge and study of data on the topography and composition of the soil. One of the objectives of these trips is to determine the exact amount of helium-3 present. To this end, the Beijing Research Institute of Uranium Geology, BRIUG, is measuring the content of helium-3 in the lunar soil, evaluating its extraction parameters, and studying the ground fixation of this isotope. These advances also reflect Beijing's overall strategy to control terrestrial minerals and metals and their use. Overall, other countries are funding programs to analyze the lunar soil, such as the future mission of the first Emirati rover scheduled for 2022. With the help of the Japanese company iSpace's lunar lander, the Rashid rover will study its geological composition and properties. These missions will undoubtedly help to assess its mining potential. Scientific missions are bound to continue over the next decade to continue surveying regolithic rocks in new lunar territories. This is an invaluable piece of scientific information that reflects one of the foundations of the human space exploration, based on the possibility of exploiting extraterrestrial resources that appear to be unlimited. In any case, the development of an extraterrestrial mining industry entails investment and infrastructure constraints. such that the deployment of existing renewable resources on Earth would remain less costly. In fact, the energy cost of lunar helium-3, from extraction to use in a nuclear fusion reactor, would make it at most a rather marginal contribution to our long-term energy needs. While existing technological and financial barriers ostensibly hinder the launch of such a venture outside the Earth system, sustained research and development policies in several countries are in this sense a way of keeping the possibility open. All in all, this feasibility could be unraveled when a technological threshold is crossed that correlates with its economic profitability. Finally, current international treaties do not provide a political and legal framework for mining activities on the Moon. In the meantime, thought must be given to the status of the celestial object, which could ultimately be like that of Antarctica, by becoming a neutral space dedicated to science.